Hello and welcome to a special lecture by world-renowned educator and esteemed YouTuber IcyGaming. Today, we'll be learning about how quantum computers work, looking at everyone's favourite approach to the problem, topological quantum computation with anyons. As always, our dear friend and marvellous assistant Jonathan the Horse will be travelling alongside us on this journey of enlightenment to help with the concepts. So, let us begin. First off, what is a quantum computer? Jonathan, do you care to explain? Nay. That's right. A quantum computer is conceptually similar to a normal computer, but has added degree of freedom in its calculation, because it replaces conventional computational bits, which are the noughts and ones you see normally with computers, and they can only ever be 0 or 1, with quantum bits or qubits, which are algebraic values that are a mix of a 0 and 1. This is a great property, but it's a little confusing. What it means is that when we measure our bit, there's actually a chance to measure it as either a 0 or a 1. It's got a chance to be both. The red line of the sphere, which represents a qubit's possible values, has an equal chance to be a 0 or a 1. So, why do we care? What's wrong with 0 or 1? Why do we hate those numbers? Having values in between suggests we can get some fancy speed up using fancy quantum computational techniques. Simply put, more options lets us use cooler logic gates, which gives us more options for speed. And speed is really cool. Take it from Jonathan. He's so fast. And come on, you've seen how cool he is. But I hear you guys. I'm listening to your microphone. This video isn't just on quantum computers, you're saying. It's on topological quantum computers, specifically the anyonic variety. Get to the point already. So I will. Firstly, why are we choosing an anyonic topological quantum computer? What does that mean? There's a lot of ways to make a quantum computer, but a lot of the methods are very vulnerable to errors. Topological quantum computers boast more resistance to error than most, so we like the sound of those. Topological computers can also be split into types depending on the shape constraints of the system. We'll be looking at using anyons, as these support a system with good error correction as well as resistance, making it even more likely to get the right answer. So, these fancy I hate ones and zeros anion-based computers are sounding pretty good. But how do they work? What even is an anion? Well, anyons are what puts the topological in topological quantum computer. Badum. Thanks, Jonathan. Oh, and they put the anyons in the with anyons. Since we understand these with topology, meaning it's dependent on shapes, would you care to help draw some diagrams on the board, Jonathan? When we think of a particle, we usually think of a tiny 3D sphere. This is the case for all particles that exist normally in our world. Anyons are a little different though, because these are two-dimensional particles. This means they can't exist normally, so we use quantum mechanics to create them by trapping 3D particles into 2 dimensions. So, what does this mean? A major difference is what happens when you swap 2 of these particles' positions, known as a particle exchange. In 3D, we can swap the 2 particles' positions like so. Easy peasy. Then we can swap the positions again to do a double exchange, so the particles are back in their starting spot. This is the same as just looping one particle entirely in a circle around the other, which is the same as not moving the particle at all. But that's not as obvious as you might think. This is only because we can keep continuously reducing the size of this loop down to nothing by lifting the loop over the other particle. If we imagine the loop is made of string, it's clear that we can just lift it up to clear the second particle, so we can shrink the loop size down to nothing. In 2D though, we can no longer lift the loop, as that requires a third dimension. So a double exchange, or what we'll call a braid, actually changes the particles, even though they're in the same place. I know what you're thinking. What happens to them? Are they going to be okay? Well, this depends on the type of anion, but it'll always be the same type of thing. We'll look in 3D to get a better feeling first. Since a double exchange leaves the system the same, or multiplying by 1, a single exchange must multiply it by plus or minus 1, because that's the square root. Particles known as fermions take the minus sign. Electrons are an example. So swapping 2 electrons leaves a minus sign at the front. It's not too important what this means, don't worry about that. For anions though, just to compare, it doesn't have to be a plus or minus 1. It could be any number, hence the name anyonic. Ha ha ha. In fact, it could change more than just the number. It could change the properties of the anions themselves. We call anions that gain a number abelian, and those that transform more dramatically by a matrix, non-abelian. For those familiar with the terms, this should be clear. To people not familiar, do not fret. The exact meanings of abelian and non-abelian aren't important. Only the way the anions transform is. But we'll talk about this later anyway. Okay, so that's how anions braid. That's cool. We're cool. Wow. So, this is some funky behavior. How do we use this for quantum computers? While you can use abelian anions for these, they can't do many calculations, so they're utterly totally useless for computers. We instead use the helpful transformations during non-abelian braiding to perform logical operations, the things computers do. These can let us perform any operation we can ever dream of, as long as it's a real operation, not a weird dream one. We know these mystery transformations are represented by matrices, but that's not intuitive when applied to a particle, and not everyone will know what that means anyway. So what do these do? We first need to learn what happens when you throw anions at each other. Well, they fuse. This means they turn into a new anion, a cooler one maybe. One anion do they fuse to? It depends on the way the anion was constructed and what anions were fused, but we always get one resultant anion out at the end of it. So what does this have to do with transformations when braiding? With non-abelian anions, the transformations that occur during braiding can make it so the anion that they fuse to changes. It's a weird concept to think about and maybe hard to believe, but it all comes from the fact that our loop cannot be shrunk down in 2D. There's a lot of maths to back this up, but you may be pleased we won't be going into this. Anyway, it's a property in particular that lets us do logic gates. For example, if the orange anion is 0 and the pink anion is 1, we can manipulate these bits by braiding. That will just swap our 0 to a 1. In practice, the braiding gives more interesting operations than just swapping from 0 to 1, but the method stays the same. As braiding is a spatial transformation, or a topological process, we can finally see where the name of this computer comes from. We use anions as topological behavior to make a quantum computer. Wow! So, that's the overview done. But you didn't click a video called IcyGaming teaches topological quantum computation with anions without wondering, how do these computers really work? I've claimed they're error resistant and even error correcting, but I've not said any more than that. I've said we can braid these, but I've still said no way of doing this explicitly. So, now we have an understanding of anions. We can begin the real explanation of an anyonic topological quantum computation. This time with real examples. Fault-tolerant anyonic quantum computers are the end goal here. This is the real advantage of using topological quantum computers over other approaches. So, how do these work? For error correcting quantum codes, we apply our anyons to a model known as the quantum double. What is a quantum double, I hear you ask? Why is it called that? Jonathan, it's time to get drawing again. Simply put, it's a lattice that we can create our anyons on. In fact, it's two. The gaps between the lattice form a second lattice. Anyons can live on the vertices or the faces. This double lattice corresponds to the name. The quantum double is defined by a group, or for those less familiar with math terminology, it's a small set of numbers that you can never escape. Think binary with addition. You're always stuck in 0 and 1. Whatever you add, you can never escape the 0 and 1. We can apply this to the binary group, but it's abelian, and we already know that that's not useful. Therefore, we won't look at the quantum double for binary. Nay. Yeah, sorry, Jonathan. I know you're excited to talk about how the quantum double for binary addition makes donut computers, but they just aren't very good. Now we have a basic understanding of what the lattices are, let's look at the simplest non-abelian group, S3. This group is actually a good pick for quantum computers using quantum doubles, so it's also a very useful one to look at. Firstly, let's look at what the group means. I mentioned before, a group is a closed set of numbers. In this case though, it's not numbers, but the transformations of a triangle. It's non-abelian because we can see if we reflect once, then rotate twice, we get the exact same triangle as if we rotate once, then reflect. So the order we do things is important. That's actually the definition of non-abelian, because order matters, and abelian means order doesn't matter. So we can see that it is non-abelian. Now we know what the group is, let's look at what this means for the anyons. For this group, we have 8 anyons, but we only need 3 of these, A, B, and C. All of these live on the vertices of the lattice we mentioned earlier. We don't have any that sit on faces. Now we know our anyons, we need to know how they fuse, because this will give us a hint as to how we can encode our data, and is important to know to help us understand their braiding, because it will change the fusion result. Here, the possible fusion results are A fused with A gives us A, B fused with B also gives us A fused with B gives us B, C fused with B or C fused with A gives us C. And then there's a bit of a wacky one. C fused with C will give us A plus B plus C. C fuses to all of them. Wow. I know what you might be thinking. Raggy, what does this mean? Well, Scoobs, it means that it'll fuse to one of any of the 3 anyons. It'll still fuse to a single anyon, and we can manipulate which it'll be, which is important if we want to code with these. Speaking of code, where are the 1s and 0s? Well, my dear viewer, we call the fusion results of the C anyon a 1 or a 0. We say that a C that fuses to an A is 0, and a C that fuses to a B is 1. We can control this fusion result by the way we create the C anyons. If we create a C anyon from nothing, they'll fuse to an A anyon. If we fuse the C anyons that came from nothing with a B anyon, then when we fuse our C's back together, we'll get a B anyon. This comes from the fusion rule of C fused with B gives us C. We still get a C back, but it's like we've hidden a B anyon inside of it. Knowing these 2 rules gives us a bit of a clearer picture of the C fused with C fusion. The C's act like a container. They'll hold any anyons that you fuse with them, and then you can open the container by fusing the C anyons back together. In fact, this analogy helps us understand what happens if we fuse another B anyon with our C that's been fused with a B once. We can only hold 1 anyon in our container, so they duke it out, fusing to an A anyon since B fused with B is A. Therefore, our C now holds an A anion. If we fuse two of these together, we'll get an A out. Remembering that A and B are 0 and 1, this gives us a way to swap between 0 and 1. Fusing a B and a C anion together is a computational NOT gate. For those unfamiliar, this is a logic gate used in actual computers. We've now recreated a fundamental part of a computer with anions on a lattice. To make a computer though, we need to create cooler stuff than that. And so we look back to the coolest part of the anions, braiding. Moving these around is a complicated process, but the end result is all that's important to us, so we can ignore this for our overview. If we remember from earlier, rewind noise. Braiding non-abelian anions, like the ones we have, or more specifically the C anion we have, changes what it fuses to. This is like swapping out the anion in our little C container for another. What does it do for our C anions though? For a C that can fuse to an A or a B, it actually mixes the two numbers up. We'll get a C that has a chance to fuse to an A or a B. We won't know which we'll get until we fuse them, but there will be a higher chance of one than the other depending on which they fused to before we braided them. If you remember from the start of the video, this is where we get the quantum part of coding from. Having a chance for an A or a B, or a 0 or a 1, means we can be partway between the two values, and that's what qubits do. So our anions can now behave like qubits. That's the fundamentals of how we code with a topological quantum computer. We just create, encode, braid, and then fuse our anions to get our logic in. By simple encoding and braiding in specific ways, we can perform any logic gate that we need. Wow! We now know what's going on in these mystery machines. How cool are we, Jonathan? Nay. I hear you, Jonathan. I'm sure our viewers are asking it too. What about our error correction? We've still not talked about it. Well, this is pretty simple now we understand our lattice. All quantum computers get errors from changes in the environment, and while topological quantum computers are resistant to this, they still do get errors. Errors on our quantum double lattice are just unwanted anions. Random background changes in the world can create anions anywhere in the lattice. From what we know about our anions though, this doesn't actually affect our data straight away, or sometimes at all. The only way for our 1s and 0s to change is by fusing B's and C's, or by braiding two C anions together. So only randomly spawning B or C anions can mess up our calculations. We've seen so far that the A anions don't do anything to our C anions, which are our data holders, so we can actually just ignore any of these. Therefore, we just need to detect any stray B or C anions and put a stop to them before they can affect our important anions. Once we detect them though, we still need to get rid of them. Our anion fusion rules come to the rescue here. Let's look back at some of the rules to see what we can do. If we get a stray B anion, we can use the fact that B and B fuses to an A to return it to an A anion. As we mentioned before, A anions can't affect data, so these are safe. Therefore, we just need to create a new B anion and put it on top of the error B anion, and we fuse them into an A anion, and that's corrected our error. But what if it's a stray C anion? We do the exact same thing. It could fuse to an A, a B, or a C, as we know, depending on what's hiding inside our C anion. So we may still have an error after the first fusion, but that just means we have to fuse whatever the result is down until we can get to an A anion. And then, again, the error is gone. So with the quantum double, or with our lattice, we can poof away any errors that arise before they can ruin our super cool, super fancy, and probably super expensive computer. Yay! So, let's have a quick recap of what we've learned today. Quantum computers use qubits instead of bits, and these can be a 0, a 1, or somewhere in between. Anyons are 2D particles, meaning they have different behavior to 3D particles when we swap them around. When two anyons collide, they fuse. Some anyons can fuse into multiple of the types of anyon instead of just one. We've also learned that if we put anyons on a lattice, we can make logic gates that support quantum computation. Quantum computers using the lattice model not only resist, but can correct any errors that occur on them. And finally, we learned that IcyGaming is a fantastic and engaging physics teacher. And with that, we did it! We have a fully working anyonic topological quantum computer. If you made it to this point in the video, well, good lord, what are you procrastinating? But we're finally at our destination, Knowledge Town. And with that, this concludes our marvelous tutorial on the topic I know you've all been desperately waiting for answers on, delivered by my favorite YouTuber, IcyGaming, and our fabulous hoofed assistant, Jonathan the Horse. Don't forget to subscribe for more unbelievably interesting physics lessons, at least in my opinion. And thank you for joining this voyage into the depths of fun physics.